Hello everyone. Benchmarking and testing in memory OLTP performance. This subject and in particular this session is very close to my heart. Last year was awesome for me. I got an opportunity to present this session in 3 conferences. I presented this at SQL Bits in England. Then in the month of August, I presented this session at Data Platform Summit in Bangalore. And then in the month of November, I presented this session at PAS Summit in Seattle. And I got a lot of emails and requests from the SQL community if I can make this session available to the larger community. And therefore I thought I should record this session and make it available to everyone. And here I am recording this session, doing all the demos all over again so that everyone has free access to this session. My name is Amit Bansal. I work for a company called eDominer Systems, and under eDominer we do a lot of things. In particular, I spend a lot of my time with SQL Maestros, where we do a lot of consulting and training on Microsoft data platform, including SQL Server. We do masterclasses, accelerators, hackathons. We have a unique learning solution called hands-on labs. For example, a lot of demos that you see in today's demo, if you want to practice them step by step, you can create your free account with our hands-on labs portal. We also have a unit called Peopleware India, where we do corporate assignments. And Expand SMERP is a homegrown ERP solution that eDominer has built since 2004. I also have a special focus on our community work that we do under Data Platform Geeks. It was formerly called as SQL Server Geeks. And apart from a lot of webinars and free events and videos that we do under the community umbrella of Data Platform Geeks, we also organize an annual conference called Data Platform Summit. It's an annual conference that happens every year in the month of August, and worldwide some of the best speakers fly down to Bangalore and deliver session at this conference. And of course this conference is very special, and it's happening this year also. As I record this webinar in Feb 2018, the conference is happening in the month of August this year, Data Platform Summit 2018. It's a 3-day conference with 2 days of pre-con. If you want to know more about this conference and what we're doing here, just visit dps10.com. A lot of people ask me what is dps10.com. So SQL Server Geeks was founded in 2010, in the year 2010, and that's why we have christened this domain dps10.com, and the conference is always going to be hosted on this particular website every year. In this conference, as I said, it's a 3-day learning event with 2 days of pre-con. The essence is some of the world's best data platform and analytics experts worldwide travel down here. Microsoft product team members from Redmond deliver sessions at this conference. The SQL Cat team, the Tiger team, they're all available here at delivering in-depth sessions. We also get very good participation from MVPs and MCMs and many industry stalwarts. And every year we focus on multiple tracks. This year we have 7 tracks and close to 100 plus sessions by almost 50 speakers. We focus on pure 100% learning, and there's absolutely no marketing at this 3-day, rather 5-day learning event. So visit dps10.com, or if you want to know more, just drop an email to contact@dps10.com and someone will revert back to you. Every year it is going to be on dps10.com. So let's see, Data Platform Summit 2019, 2020, 2021. Of course, we will hopefully carry on that long. Just visit dps10.com. My name is Amit Bansal. I work for eDominer, and specifically I have a focus on SQL Maestros. I started working with SQL from late 90s, and I started my career as a developer and then moved on to becoming a database administrator. But from 2005 onwards, I started focusing a lot on performance tuning and optimization. And since then, I have delivered more than 600 assignments for 200 customers globally. All sorts of work related to SQL performance tuning, query tuning, optimization, benchmarking, baselining, mentoring and training thousands of SQL professionals worldwide. I'm a Microsoft Certified Master of SQL and also an MVP awardee from Microsoft. Apart from my day job, whenever I get an opportunity, I speak at global conferences, and thankfully I've spoken at almost all global conferences, including SQL Bits, PAS, TechEd, and which is now called as Ignite, and of course our own Data Platform Summit. That's the URL, sqlmaestros.com, where you could visit and learn more about me. What are your takeaways for today's session? In today's session, I am going to talk about the performance principles of in-memory OLTP, benchmarking performance. How can you do that? How do you simulate near real workload, and identifying good and bad candidates for in-memory OLTP? But let me begin with a bit of background. So in-memory OLTP was launched as a primary feature, as a premium feature in SQL Server 2014, and when I saw this feature for the first time in demos by product team members, and when I tried it myself with some examples, I was completely blown away. This feature to me looked so promising because it was actually able to deliver great performance improvement throughput for transactional workload, and I was like, this is going to be a game changer. But as years passed by, we had SQL 2014, and then SQL 2016 came, and of course now we are probably working on maybe SQL 2017 and even looking forward to SQL 18. I saw that the adoption of this feature is not all that great or all that high as I had originally thought, and I was wanting to know as to what really is the reason, what's going wrong, because two features really caught my attention. One was in-memory OLTP and the other one was column store index, and both of them looked really promising. So I actually started visiting a few customers. I mean, of course, all my Ivy League customers. I started talking to them that, hey, have they heard about in-memory OLTP? Have they tried it? Have they done some POCs? And I got mixed response, less positive, more responses were like that they tried to do something, but they weren't really happy with the kind of performance improvement they were getting, or they just did not do things the right way. And I wanted to investigate a bit more because I was really curious, as I said before, that this feature was superb. I mean, it really offered that extreme transactional processing capability. And then in every visit to my customer for any assignment, be it consulting or training, I started talking to senior DBAs and principal DBAs, and of course the team leaders and the database managers, to see what have they done with this feature. And customer by customer, I started gathering a lot of information after talking to them, after seeing what they have done, and I came to a conclusion that most customers, most POCs that were done, they were actually not done in the right way. There were a few things that they did not do right, because of which they were not able to see that kind of performance improvement, which are some of those guiding principles as to why and how will you get performance improvement with in-memory OLTP. And then after my learning, I created a lot of academic prototypes, which now I'm going to present to you in this video, and of course is what I presented in all those previous conferences. So I learned the hard way what customers are doing wrong. They have a very genuine need of something like in-memory OLTP, and they can really gain a lot of performance improvement, but provided they do things the right way. So, and in the next 1 hour, that's what I'm going to talk about. So what are your takeaways today? You are going to understand how exactly in-memory OLTP gives you that kind of extreme performance improvement for your transactional workload. How do you get that high throughput? That's what you're going to understand. And the crux of that is latching. We will talk about this as we move forward. Then you're going to see benchmarking performance. What are the tools and techniques that you can use to benchmark performance? Now, this is something that I do day in, day out with customers, and I use all simple utilities like RML or Excel to record all our numbers and to do all the mathematics. So I'm going to show you very simple techniques. I don't believe in making things complicated. I will show you all these techniques on how to do benchmarking and baselining. The third thing that you're going to learn is how to simulate near real workload. Now, most of the times when you are testing, specifically when you're doing this performance stuff with, let's say, in-memory OLTP or column store, or in general, you always got to simulate near real world workload. You can't test, or you can't do your POC, or you can't do your performance benchmarking with empty tables or tables with less data. You really need to have large tables, big tables with a lot of data, and you really need to simulate your workloads with hundreds and hundreds of users. I have seen these customers testing their or doing their benchmarking or baselining with less number of users, 5, 10, etc., and manually running scripts. you just will not really get the right output that you are expecting. So you have to simulate and generate that real workload. It's not so easy, but you have to come close to what really your production environment is like. The biggest mistake we do is production environment is very different compared to your test or dev environment. But when it comes to doing some real stuff, you got to make things as close as to production environment. And of course, the final crux of all this is going to be, you're going to identify the good and the bad candidates for in-memory OLTP. Now, in-memory OLTP is not a magic bullet that you implement and every transactional workload is going to get awesome performance improvement. It wouldn't work that way. You need to understand the performance principles of in-memory OLTP, and then you will be able to infer as to which candidate is a good potential candidate for in-memory OLTP and which ones are not. So hopefully after this session, you will be able to figure that out yourself. So let's get down to demos. The next 1 hour is all going to be demos. The demo is divided into 3 parts: part 1, part 2, and part 3, and there are respective folders for each part. Before we begin with part 1, I will navigate to C drive and create 2 folders for the purpose of demo. Data files is my first folder, and then I create another folder called SQL Maestros. These are the folders where I will store some files. Back to the demo folder, part 1, I will first open one_setup.sql. The files have been named nicely in the correct order so that you can reproduce this demo in your own test environment. One_setup.sql will create a few tables. Before we run the script, I go to query, run the script in SQL CMD mode because we are doing some variable assignments, etc. Now you will notice that I'm using the database AdventureWorks 2012, and I'm sure you are familiar with this database. In this script, we are creating 2 sets of tables. The first set of tables are all memory optimized tables. They have a suffix _in_mem, and you will notice that these are memory optimized tables. As you scroll down, you will see this clause which says memory optimized equals to on, and some of them will have bucket size, etc., which are the requirements for creating a memory optimized table. So you have sales order header in mem, and as we scroll down, you have sales order detail in mem. These are all suffixed with in mem, and they're all memory optimized tables. You can see again bucket count and memory optimized equals to on, so on and so forth. As you keep scrolling down, you will come across many of these tables. So there are a bunch of these memory optimized tables, and then you have same set of tables which are on disk, which is traditional disk based tables. Now of course these are traditional disk based tables, so there's nothing unique about them. They're just normal tables. So what are we doing in this script? We have 2 set of tables, memory optimized and disk based tables, and their schemas are exactly the same. And now you can understand what are we trying to do. We will try to run scripts and stress SQL Server and insert data into these tables and measure performance, disk-based table performance versus memory optimized table performance. Let's go ahead and click execute and run this script, and wow, I get an error because something might be highlighted. So I will just quickly go and click somewhere else and click on execute again. There you go. While this is running, I will open the next script, which is to_setup SPs. So I think this one is done. The first one, commands completed successfully, so the tables are created. Let's close this. In to_setup_SPs, I am creating a set of stored procedures. The most important stored procedure for you to notice is, as we scroll down, is this one, USP_demo insert sales orders. It's a simple stored procedure which we will call, and it will insert data into those tables that we have created. Now the only catch here is we have a parameter here in the stored procedure called useInMem, which is of type bit and takes a value of either 0 or 1. And the idea is very simple. If we pass a value 0, the data will be inserted in disk-based tables, and if we pass a value 1, data will be inserted in memory optimized tables. So we are going to call this stored procedure once for disk-based tables and then again for memory optimized table to measure performance. Let's go ahead and create these stored procedures. I click on execute and those stored procedures are created without any error. Let's close this. Now I will move to the next one, 3_fire, and I will open this. Now let me explain you what are we trying to achieve in this particular script. Use AdventureWorks, execute. Now you will see that there is an on-disk test and in-mem test. In on-disk test, we are going to execute this stored procedure that we just created in the previous step, and we are passing the parameter 0 because we want to insert data in disk-based tables, and we are inserting 100 records. And in the in-mem test, we will do the same thing, but the only difference is use in-mem we say equals to 1, which means we are going to insert data into memory optimized tables. Before we do this, I have another script here which is called as monitor.sql. This is 5_monitor SQL. Let me open this. I use this script for monitoring purpose, and I am not going to run all of this right now. I will use this in part 2 and part 3, but for this part 1, which is a very simple demonstration of in-memory versus disk-based, I'm just going to run this to show you that right now both the disk-based tables and the memory optimized tables have no data. Let's go back to Fire, and you got to be a bit careful here as to how many orders you want to insert. Now I am running on a 8-core VM with 32 GB RAM, and I am using solid state drive, so things might run much faster. So if you are trying this demo on your machine, you may want to play around with this number depending on what is the configuration of your hardware. So I am going to put down, let's say, a number called 5000, which means 5000 orders are going to be inserted both for disk based and then 5000 orders for memory optimized. And let's get started with the first test. So I'm going to insert this data, 5000 orders, one user, 5000 orders are going to be inserted in my disk based tables, and I click on execute. While this is running, I will open my Excel file where I do some performance mathematics and benchmarking and baselining, whatever you call it. In this Excel file, I am going to record some performance data. So I will go to the first sheet called good, and the idea is very simple. This test is being done by one user right now, and I'm going to record number for disk-based test as well as in-mem test. And then the D column, this particular cell, will give me the performance improvement that I see between disk and in memory. Let me go back to SQL Server and see if execution is done. Yes, execution is done, and 5000 row insert takes about 21 seconds. So look at the status bar there, 21 seconds. Well, you could always use set statistics time to be more precise with the execution time, but this is good enough for the purpose of demo. I will go and record 21 here. So this takes about 21 seconds. Now back to the script. I am going to execute the same test, but this time, as you know, I am going to insert data into in-mem. But before I do that, let's go back and look into the monitor where we are checking the count of records in each table. And when I execute this, you can see we have 24,000 records in our order detail, and we have close to 5,000 records in our on-disk tables. And of course, in-mem tables are blank. Let's go back here and execute this one. Now I've still not got into technical details. I'm still just running scripts, inserting data to see the performance. And part two is where we will dive technically deep into in-memory tables as to why and where do we see performance improvement and all the technical aspects related to weight types and latch contention, etc. So just hold on for a moment. Let's record some numbers. Now, very interestingly, when you run this one, it takes about 23 seconds to execute. So if you look at the status bar there, it is 23. Let's go back and put this number down here. Now you will be surprised to see that with one user, disk based takes 21 seconds, in-mem takes 23 seconds, and which means this is a negative performance degradation of close to 8%. So you see a value of minus 8%. Now, practically speaking, you might not really see something like this. Practically in real world, when you're running scripts or workloads, you might see slight performance improvement with one user close to 5% or 10%, or both the execution in memory world versus disk based tables would be more or less same. And in fact here also it's more or less same. It's just the system is very dynamic, so you can always see a difference of a few seconds. So 21 versus 23 seconds. What is the conclusion? The conclusion is that you just don't see any performance improvement with disk-based table versus in-memory tables. Let's go back and look into our monitoring script, and I will execute both of them again, and you will see now equal number of records exist in both the tables. So if you see sales order detail 24,000 and sales order detail in mem 24,000, and you have sales order header on disk 4,999 and sales order header in mem 4,999. Equal amount of data has been inserted in both disk-based tables and memory optimized tables, but you just don't see any performance improvement. Now, problem number one, most customers will test their workloads with a single user and come to a conclusion that memory optimized tables is not really doing any good to their transactional workload. Now, I want to elaborate more on this, but let me move to part 2 of the demo. In part 2 of the demo, I'm going to dive deep into weights, I'm going to dive deep into latch and where do you really see performance improvement, and then we will compare part 1 with part 2 and see where our customers are going wrong when they are testing in-memory OLTP or the performance of memory optimized tables. In part 2, unlike part 1, I am going to simulate more than one user, and for that purpose we are going to use a utility called RML Utilities. RML Utilities is developed by the SQL team and is of course fairly reliable, and when you install this utility, it's available in the installation folder when you download these files. I have already installed it in the default installation path, which is Program Files Microsoft Corporation RM Utilities Utils. And it has, when you install, you will get an exe, an executable called ostress.exe. ostress.exe is the utility which can be used to stress SQL Server with X number of threads, like you could specify 100 users or 500 users, so on and so forth. Back to the part 2 folder. In part 2, now you don't need to really run 1 underscore and 2 underscore because that has already been done in part 1. We'll straight away open 3 underscore fire. I will go back and open monitor.sql. Then I will open order insert and then weight baseline top 10. So I'm going to use a couple of these scripts. Please bear with me because I'm going to shuffle between screens and scripts, so try to please keep a track of that. Let's first focus on order insert. If you remember, this was one of the scripts that we ran earlier in part 1, and now we are going to run this again, but this time this order insert.sql is going to be called by ostress utility. So if I go to my fire.sql, here is the command ostress-e, which means it stands for trusted connection, input file -i, which file? Order insert.sql. So this is the file here that I'm going to paste inside the rm utils folder, quiet mode -q, and then we are going to simulate 100 users. 100 users will call this particular script and will execute whatever is there inside this script and is going to repeat then 10 times, and that's what -r stands for, which is repeat, and that's the path of SQL Server -s. So let's close this order insert.sql, and I'm going to take it from here, order insert.sql, copy it and put it in rmutils folder here, so that it just becomes easier. I don't have to supply the full path. ostress.exe will call order insert.sql. I'm going to double click order insert.sql and open it from here if I have to make any changes. And just like last time, we will first insert data into disk-based tables, 100 users, each user inserting 100 records and repeating 10 times if you recollect the command. And then we will change it to 1 to simulate memory optimized tables. Let's keep this on. When we go into monitor, I have already truncated the tables. If I execute this, I get an error, which is nice. Let me just change the database context to AdventureWorks 2012 and execute this again, and you will see all the tables are empty. Now, because in this particular demo, part 2, I am going to dive deep into in-memory OLTP concepts, and I'm going to talk about wait types and latches and latch contention. I first want to clear the cached data about latches and wait stats. So here is the command dbcc perf, clear the latch stats and clear the wait stats. Let's execute them and let's quickly verify. If you run the dmv sysdm os latch stats, you will see all 0, which is all cool. And if you run the wait stats dmv, you're going to see very low numbers. This is what you expect. So we are all set for part 2, looks like. And I go to fire, and this is the command that I am going to copy and fire it from command prompt. So I will launch command prompt cmd. This is my command prompt. I will navigate to the rmutils folder, which is cd program files, and then cd Microsoft Corporation, cd rmutils, and cls, clear the screen, and right click, paste the command. Let's verify rmutils ostress-e order insert.sql, 100 threads, repeat 10 times, and that's our path. And let's verify again. We are first inserting data into disk-based tables, and as you know, latch stats and wait stats have been cleared. So we're all set. Let's go and press enter. And now threads are being created and 100 threads are created. While data is being inserted, let's go and do some monitoring. Now on line number 11 here, I am going to look at waiting tasks. So this is the DMB, which will show me that all the threads that are running, if they're waiting on something, and you can see many of them are waiting on page latch underscore up, which is update. And as you keep running it, you will see there is of course a lot of latch contention, which is clearly visible. There are a lot of waits happening on latches, and you could further verify that from another script here on line number 18, os latch stats. And as I run it, you will see, observe this count, which will keep on increasing, which means there are a lot of latch counts, latches happening, and the count is constantly increasing. So you can understand what I'm trying to show you here is right now data is being inserted into disk-based tables, and there's a lot of latching going on. And why? Because there are so many different users, 100 users trying to insert data. Now looks like the latch count has gone static, which means our workload might have completed. If you look at waiting task here, now there's nothing really waiting. So let's go and look into the command prompt, and you will see that execution is indeed complete. And I want to figure out how much time this has taken. So elapsed time, it takes about 1 minute 1 second. So that's close to 61 seconds. Now I'm going to record this number. I will go to the Excel file. For 100 users, disk-based tables, it takes 61 seconds. And you know what I'm going to do now is, let's go to baseline here, and you remember we had cleared the wait stats as well. And when I run this now, I'm going to look at my top weight types, and you can see my top weight types are page latch ex, page latch up, which is for update, and page latch shared, which means there was a lot of buffer latches, there was a lot of latching contention. And let me just quickly copy um, just this much data into Excel again. In Excel, I have another sheet here called weights where I'm going to paste this data. This is for 100 users, and these are our numbers. Okay, so back to the monitoring here, and want to show you that data has been inserted into disk-based tables, but our memory optimized tables of course have no records because we haven't run the script as yet. Now this leg 2 of part 2 demo is to insert the data into memory optimized tables, and as simply we just will say use in mem equals to 1 and save the script, which means now the same command, if we fire again, we will insert data into disk-based tables for the memory optimized tables. What do you want to do here is do we really want to clear the latch? Now if you look at the latch statistics here, and as you see the big numbers here, let's go and clear weight stats and latch stats again because we are retesting things again. We're all set, and I will just press the up arrow and I am going to get the command back again and press enter, and you know this time data is going to be inserted in memory optimized tables. 100 threads are being created again. Each thread is inserting 100 orders, repeating 10 times. Now as you go and look into waiting tasks while the workload is running, you are not going to observe any waiting thread on latch. You can see it's all blank. Earlier you had seen a lot of records, a lot of threads waiting on latch. And if you look at latch stats here as well, you're hardly going to see any number here because there is no latches at all, no latch contention happening at all. And let's go back and look at the command prompt, and you know what, this is done. So the execution is done pretty fast, and it has taken about 26 seconds to execute, and you can observe this here. Now I will go back into the Excel file, and I am going to go to sheet good here, and I will put down the number 26. Now you can observe 134% performance improvement versus a degradation of -8% in the previous case. Let's go and run our monitoring script once more just to be sure that we've done things all correctly. So execute, and you can see the same number of records. Both the disk-based tables have 495k records, and both the the corresponding disk and in mem have 495k records, and the order header on disk and in mem have 99k records. All good. So this is our part 2 demo where you see a performance improvement of 134%. Now let us understand what has really happened. Why did we get this kind of performance improvement with 100 users, and in the previous case we just did not see any performance improvement? Let's try to decode and understand. So traditionally SQL Server has a latching concept. Now what is this latching concept? SQL Server data is stored in pages. A page is 8 kilobytes. Now that is the lowest storage unit in SQL Server. Data is stored in these 8K pages, and they are on disk. When SQL Server has to read or modify data, they have to first get these pages from disk into memory. Now let's specifically talk about modifying data in these pages. Before SQL Server attempts to modify data in these pages, SQL Server has to acquire a latch on these pages. Now what is this latch? Latch is a lightweight object, and it could be comparable to a lock, but lock is more logical and is at transaction level. So while locks ensure transactional integrity, latches ensure physical integrity of the page in memory. So before SQL Server attempts to modify the page in memory, it holds a latch, which means if a lot of threads or users want to modify data or insert data in the same page, they will have to wait in a queue, and that is why you see those wait types like page latch up, page latch sh, and page latch ex, which means they are waiting to acquire a specific latch. And this is called as latching contention, because at any given point of time only one user can hold a latch on a page to modify the data on that page, and once the job is done, the latch is released and the next thread gets its turn. This is the typical latching concept in SQL Server. When it comes to in-memory OLTP, in-memory OLTP is a latch-free design. There are no concepts of latches. Now, this is interesting as to how does in-memory OLTP work. Well, in very simple terms, this is the guiding principle of in-memory OLTP. It's considered in-memory OLTP as a parallel engine that is running to the traditional database engine, and data is stored in file stream. So there are no pages, there are no 8K pages, and there is no latching concept, which means integrity is maintained using multi-version concurrency control system. So if you see, the architecture is completely different. No 8K pages, no latching, and maintaining multiple versions of the record is automatically done by snapshot isolation. So while we talk about the latching concept and in-memory OLTP giving you so-called transactional performance improvement with a latch-free design, it is also important to note that in-memory OLTP will only improve performance for your transactional workload. It will help improve the throughput of your transactional workload. It is not meant or designed to improve performance of your read workload or queries that have like select statements. So queries, DML statements that have like inserts, updates, and deletes are the perfect candidates to gain performance from in-memory OLTP design. And I have seen a lot of confusion with customers here, because column store index and in-memory OLTP both offer performance improvement, but as I want to reiterate that both of them have different purposes altogether. While column store index helps improve performance of read workloads, select queries, in-memory OLTP is designed to improve performance of your transactional workload, or in other words, improve the throughput of your transactional workload. Now, coming back to our numbers, when we ran our workloads and we were testing with one user, you did not really see any performance improvement. That's precisely the point, that with one user there was absolutely no latch contention, or even if there was, that was minimal. With 100 users there is latch contention. Now, as I get further into the explanation of the concept, why not even test this with 500 users? And all I need to really do is back to SQL Server here and order insert. Let's first insert data into disk-based tables, and I'm not going to monitor again because you have really seen it, but I will just go here and change N100 to N500 and insert data into disk-based tables, which means now 500 users, each of them are going to insert 100 records and repeat 10 times. Of course, this is going to take a bit more time, but let it run while we talk about performance improvement. So back to the Excel file. Now, this is the first mistake that I have seen most customers doing, which is they kind of probably have not understood the chief tenet, the chief architecture of in-memory OLTP as to how does it improve performance and what kind of constraints or issues is in-memory OLTP trying to address. Well, in-memory OLTP has a lot of other things like natively compiled stored procedures, reduced logging, and there are areas where it offers benefits, but where you see the kind of magnitude of performance improvement that you expect is because of this latch-free design. Now, most customers will test their workloads with one user, and then they would come back and probably complain, hey, you know, Microsoft demos really run so well and we saw 40x 50x performance improvement, but when we try to do it in our environment, we hardly see any performance improvement. That's because they have not tested correctly. They have not benchmarked or baseline in-memory OLTP performance correctly. In order for you to really see the power and performance improvement offered by in-memory OLTP, you have to test with lot of users. Hundreds and thousands of users is what you should be testing with to see the real magnitude of performance improvement that in-memory OLTP can offer, and that can only happen when you increase and scale up with number of users. That is where you are going to see latch contention. So in-memory OLTP addresses the latch contention problem, the latch contention issue. And if you have a SQL Server environment where there are tables that are suffering heavily from latch contention, then in-memory OLTP is a perfect solution for that kind of environment. Let's go back to the command prompt. Okay, this is still running, no problem. I have another query that I wanted to run, and this is manually analyze DMVs. And if I take the second one here and I execute line number 20 to 31, and let's execute this in AdventureWorks 2012 again, and I do this mistake all the time. And you can clearly see that SQL Server itself tells me that there are few of these tables like sales order detail and sales order header which have maximum latch contention. So this is the most common question that customers will ask, that hey Amit, how are we going to identify which tables have maximum latch contention? Well, use this script, because look at this DMV, sysdmdb index operational stats. This DMV will keep track of the operational statistics of a particular index. So I mean, it says index because we're going to have clustered index on the object, or non-clustered indexes. So clustered index is the data, so it's going to keep track of the latch statistics. Just run this DMV and you get to know all the tables that are suffering from heavy latch contention. Let's go back and look at the DM query, and looks like this one is still running for 500 execution. I have the number already recorded, so it took about 241 seconds early on, so maybe we'll wait for a few more seconds. So the summary here is point number 1. After our part 2 of the demo, first things first, do not test in-memory OLTP with just a few users, 1, 5, 10. No, you got to scale up and test with maximum number of users that you can. At least you have to increase the number of users to what your real world environment looks like. Point number 1. Point number 2 is you have to test with huge amount of data. You just can't test with small set of data. You again have to make it as close to real world as possible. And weight stats play an important role here, is because which is what my part 3 is going to be about, is you have to see what are your top weight types, because your top weight types give you indication and hints as to where there are performance bottlenecks in SQL Server. And my point here is that if my latch weight types were not top weight types and there was something else coming in my top 10, then probably I would first want to address them before I get into latching issues. So that is why I have recorded weight stats here, because I'm going to run part 3 of the demo and compare, and then I will show you what the difference is. Let's go back to the command prompt, and I see that it's still running. That's quite a bit of time. Okay, so well, let it run for a few more seconds. Now, before I jump into part 3 of the demo, in part 1 I showed you something that wasn't working. Part 2 is where it worked and you got the performance improvement of like 134%. But now you see from my previous runs, I have recorded the numbers. When we were doing this with 500 users, we got a performance improvement of 630%. Now that is huge. That is like 6x and more when we scale up more and more users. Now this workload, these set of tables were like kind of perfect candidates where I could get magnitude of performance improvement with in-memory OLTP. My DMV shows tables with heavy latch contention. My weight stats show me that latches are top weight types, and my test shows me that I can really get good performance improvement. In part 3, I am going to show you workloads and tables where probably in-memory OLTP will not be the best tool or feature to use to get performance improvement. Problems and performance bottleneck lies somewhere else. You got to first fix that before you can get any performance improvement with in-memory OLTP. So this, as you know, is these are the takeaways that I'm actually going to I'm talking about. Understand the guiding principles of in-memory OLTP performance as to where it improves performance and where it doesn't. Understand how to baseline and benchmark using these utilities and simple Excel formulas and Excel sheets. How to stress number of users using RML utilities. Well, this is what really the session is all about. Great, and we are done here, and now you could see, well, this took a lot of time, much more than my previous run. 5 minutes 38 seconds. So this is 5 into 6, 338 seconds. So I am going to put this down here, 338. And what if I will, before I close part 2, run the same piece of demo with in-memory, which means I will go in order insert and change this back to 1 and save it, and look at the performance improvement with 500 users now inserting data into memory optimized tables. RML Utilities is a wonderful tool, and I just really love this tool, even though it does not offer any graphical user interface. Really helps simulate very well. So you could clearly see that we now have 500 threads here that are being created, and they are inserting data into memory optimized tables. I have not recorded wait stats again, not really required, because I just wanted to get the concepts across to you. And with our 100 users that we ran before, we have got these numbers. Now please keep an eye on these numbers. Write log is 156k in terms of count. Well, another point that I want to make here is recording the wait stats is not really as simple as what I'm showing you here, which is we just take the wait type and the count. Well, we want to do some more mathematics on it, which is take some percentages, or along with count, you also want to take wait time in millisecond. And we generally store this data in baseline databases and filter on time factors, that is from like morning 10 to 12 and things like that. Well, all that is beyond the scope of the session, but I just want to get the concepts across to you, not necessarily this is how exactly we are going to do in our test environment. My point is we want to do a little more things. So well, fantastic. This is done, and OSTRESS utility execution is complete, and this time it has taken 43 seconds, as you can see. So what I'm going to do is record 43 here, and let's look at the performance improvement. This is what you get, friends. 686% performance improvement with 500 users. Now the story is right in front of you, and you can understand what works and what doesn't work. Why did customers complain that in-memory OLTP did not really give them the kind of performance improvement they were expecting, or the kind of demos that they had seen, etc. Now remember, these demos and the concepts that I'm talking about are not really super advanced. They're fairly basic and at intermediate level, what we read and what we hear, but I'm trying to show you practically where customers go wrong, and this is just one portion. Now I'm going to show you in part 3 where well, customers are doing everything fine, which is like 100 users and 500 users. They have got that thing well, but probably their workloads and tables are not tuned enough, or are still not ready or fit for in-memory OLTP, or performance bottlenecks are somewhere else, but they're still looking at in-memory OLTP without really going and fixing that performance bottleneck. So we are going to look at that now in part 3. Let's begin with part 3. In part 3 folder, you have bunch of scripts again, and this time we are going to do a new setup. So I will double click one_setup SQL, and I'm going to set up a new database with a new set of tables. So I am creating a database called IMOLTP, and this database contains a file group which contains memory optimized data. So as you might know that to store memory optimized data, we need to have an exclusive file group, a separate file group. We'll create that, and then we add a file to it, and this is where we store the file in SQL Maestro's folder that we had created initially. execute this. Let's use OLTP, execute. And we are going to create a table here, which is sales order header again on disk, and then we have the in-mem version of it. Now in on disk, I want you to take a special note of a few things. First, you will see that sales order ID has the data type as unique identifier, and we have created a primary key on it, and by the virtue of that, there is a clustered index on sales order ID. Now please keep this in mind, because we are going to look into this again. We will come back and talk about the implication and significance of having our clustered index on a column which has unique identifier data type. I've also added two more columns here, comment and remarks, of char 100 each, though I'm not really going to store 100 bytes in that, but just to quickly fill up the pages and the data, I have added these two columns. So let's go ahead and create this table. So there you go, execute, and likewise we create its corresponding in-mem version, which is the memory optimized table. Same schema, same structure, execute, and we are done. Likewise, we will create a stored procedure which was going to insert data into these tables, and it follows the same logic as before. We have a parameter use in mem, so if we pass value 1, it is going to insert data into memory optimized table, and if we pass a value 0, it's going to insert data into disk based tables. So we execute this, and the stored proc is also ready. And if you look into these two tables, now they don't contain any data. That is our setup. Let's close this file and open the remaining ones now. To underscore order insert. Now this is the file to underscore order insert that is going to be called by RM utility executable ostress, and the same logic again. So as you know, we are going to copy this file and put it into RM utils folder. There you go, and I'm going to open it from here because we are going to make changes to this. What about the other ones? Other ones is 3 underscore fire, and then we have 5 underscore monitor, and then we have our baseline. So let's go into 3 underscore fire, use in mem OLTP, and what are we going to do? First step is we are testing again with 100 users, and then we are going to test with 500 users, and we will do both disk and in mem version. Sorry about that. Let's go to the Excel file and see the sheet says bad. Now remember, this is not really a bad workload as such. No workload is like bad as such. I am going to show you that when you talk about this particular workload where you see the schema is a bit different, and now when we do our testing the numbers are going to be different, we will investigate and find out that this workload is right now not a good fit to be moved into in-memory OLTP or work with memory optimized tables. So we have now let me just explain you the sheet a bit. In this particular sheet, what I am trying to do is these set of tables have their clustered index on GUID, and I have highlighted GUID as with orange color, and with GUID I have a test of 100 users and 500 users, and then I am going to change the clustered index from GUID to order date, and I've highlighted this as green, and then I'm going to test again with 100 users and 500 users with order date as clustered index, and we will record our numbers. So let's go ahead to SQL here, and let's copy. So first test is with disk based tables. That's fine. So we save it here. We go to fire, and this is the script we are going to copy. So I copy this and I go to the command prompt. Let's clean this, paste the script here, and notice we are again going to test this with first 100 users. That's what we are going to do. Before I fire, as we know, we want to clear of the weight stats and latch stats because this is a fresh test that we are doing. So we want to compare the numbers and record everything all over again. So let's execute this, and to confirm, your OS latch stats is showing all 0 and your weight stats are showing all no numbers. Perfect. We seem to be doing good here now. Ready for the test. And we press enter. Test has begun. While the test is going on, and if you see, nothing different. We are doing exactly the same things as we did before. If we look into the waiting tasks now, there are some weight types being assigned to our threads as we move, as the workload is running. You will look at latches happening and big numbers for latching as before. So you're seeing more or less the same things happening again. But hold on just yet. We want to really see if this candidate is a good candidate for in-memory OLTP. Back to the command prompt, execution is done. And if you look at the elapsed time, it has taken about 29 seconds. So let's go to Excel and record this here with GUID 100 users. It has taken 29 seconds. Now I am going to look at my weight statistics. You remember we recorded this for 100 users in the previous demo also in part 2. So when we run this, we are getting a few things here. So let's copy this, just maybe top 5 or top 6, and go back to our Excel, and let's go and paste it here. Now we will come back to this in a while, but initially, with the first glance, you notice that you are not really getting the 3 page latch weight types on top. Here your top weight types actually are something else. In fact, write log is the topmost weight type here. Now this is really going to be an interesting observation. Also, if you see the amount of the write log weight type count, the occurrences are lesser. Earlier we had like 156k and you have 116k here, but despite the occurrences are less, it still is the top weight type. Now which means something is going wrong there. There is something that we need to observe. So we will come back to that in a moment. Let's go ahead and do this test now with in-mem. So with memory optimized table, I just change the bit value to 1, save it, and let's go ahead and fire this again. And this time this is attempting to create 100 threads and insert data into memory optimized tables. Interesting observations are on your way now. I really don't need to test much. I mean, we know that we are not really going to see any weight here because this is going to be latch free design. But yeah, there's something you might observe as we complete this. Done. This is done quickly, and you can see the time we take now is 17 seconds. So let's go back to Excel and record the performance here as 17, and you see a 70% performance improvement. Now in the first glance, if I compare our part 2 with 100 users, we got a performance improvement of 134%. And here with the same workload, similar workload, we get a performance improvement of 70%. But what is the scene with 500 users? Now this is what we want to test again. So what I am going to, now this is really all about numbers. I'm not going to go into weight stats again or latch stats again or show you waiting tasks again. This is something that you know already. So I am going to now test with 500 users. Put this back to 0, which is insert data into disk-based tables, and let's change N100 to N500 and press enter. Now 500 threads are being created and we are inserting data into disk-based tables. While this is running, of course, you will see weights happening. Oops, sorry, I wanted to see the latch counts. Okay, climbing up. Now, to me initially, if I see numbers for latch counts are not really very high. Okay, there are few latch weight types there coming up, but something else is happening, and this is what I really want you to observe. A lot of different weight types that you could see. Now let me see the workload is executed. Elapsed time is 37 seconds. Now as I record this number 37, let me quickly fire this for in-memory OLTP also. So we go to SQL Server. Remember, this is 37 seconds. I'm going to change this back to 1, which is insert data into memory optimized tables, and go ahead and execute this. 500 users are now inserting data into memory optimized tables, and let's go and record the number here. For 500 users, we got 37 seconds. Now what do we really get for in memory? This is going to be the decider when we are doing our performance testing, baselining and benchmarking our numbers. I hope all this while you are getting the sense of how we are testing various numbers with uh, X number of users. We are scaling up and we are doing various permutations and combinations. Well, baselining and benchmarking is really all about testing various permutations and combinations and recording your numbers to see where you're getting performance improvement or not. And this time this executes and takes about 38 seconds. 38.9, so that's close to 39, but no problem, we put 38 seconds. Now if you look at this, with 500 users you have got no performance improvement, -2%, but let's just say that you did not get any performance improvement. This was really flat compared to our previous run, where with 500 users you get 686% performance improvement. Now this is the crux. What's going on? Similar example, similar schema, and we're doing exactly the same thing, but this time in-memory OLTP does not give you any performance improvement. So this is a workload which is right now not a good fit for memory optimized tables, and that's why we call this is a bad candidate. Not really a bad workload, but a bad candidate for in-memory OLTP. And I have seen customers doing stuff like this, where they have a candidate which is still not a good fit, and they say, hey, in-memory OLTP is not a great feature right now for us. It's not just giving us the kind of performance improvement we want, without realizing or without investigating as to why is it not really giving you the kind of performance improvement you want. So now I will show you why you did not get performance improvement for this workload, and in part 3 of our demo. Well, you know, the answer lies here. Your bottleneck is not latching. Latching is a bottleneck, but before that you have your topmost weight type as write log, which means performance bottleneck in SQL right now. With this small test that we have done, you first got to fix write log. If you fix write log first, then probably your latching contention comes as the topmost contention, and probably your workload will benefit from in-memory OLTP. But right now, write log is the main bottleneck that you got to fix. In our previous runs in part 1 and part 2, you saw that latching was topmost. So it was clear. SQL Server was telling us that, hey, I'm really suffering bad from latching, so let's go ahead and try to fix that. But right now that's not the case. So what is write log doing here, and why it pops up here before latches? The reason is that we have our clustered index on unique identifier data type. Now, which means that let's get into some basics of SQL Server internals here. Clustered index means data is sorted on that particular column, or by that particular column. And when 500 users insert data into this particular table, where order ID is the clustered index and there is unique identifier, every time a new record is inserted, a new GUID value is generated. And because there is a clustered index on this GUID value, every time the next GUID value is generated, there is no guarantee that the value is lesser or higher than the previous GUID which was generated, which means across the table, across the pages, you have random GUIDs being inserted. There is no serial order, or it's not ever increasing in nature, because the next GUID, every new GUID that we get, there is no guarantee whether it is higher or lesser than the previous GUID. So it's random insert across the table, across the pages, which means earlier, when in part 2 of our demo we were inserting data, it was ever increasing, which means all the inserts, all 100 and 500 users are hitting at the end of the file on the last few pages where you could see a lot of contention. But now the contention is spread across the file, it is spread across the pages, which means that you are able to write more, which means the speed of writing onto these pages seems to be faster than the latch contention itself. That's why write log comes on top, because you are able to insert and write more data. Why? Because you're touching more pages now compared to the previous demo. In the previous demo, we were only touching a few pages at the end of the file and we had a long queue. Right now we have queue, but the queue is spread across the file, it is spread across the pages. That's why write log comes on top. And that is precisely the reason why in this particular example, you got to first fix write log, which means maybe investigate into moving the log file on a faster disk and things like that. Well, that's beyond the scope of this session as to how you could optimize your log, but that's where the bottleneck is. So you got to first fix that, then only you can get benefit from in-memory OLTP. Now, if your bottleneck remains to be write log or any other wait type, until and unless you don't fix that, you're not really going to get any benefit, or you may just get marginal benefit by moving into memory optimized tables. And you can clearly see the demonstration with 100 users. When the contention was a bit less, you still got 70% performance improvement, but when you scaled up to 500 users, you have got no performance improvement at all. And look at the contrast here, 0% almost. So -2, let's say, like it was like all flat compared to previous run where you got 686% performance improvement. Well, that's really the crux. Now, if you go and look into wait types, someone pointed out earlier that if you see write log here, we had 156k count and here it was 116. Well, in-memory OLTP benefits from reduced logging. For example, indexes, changes to indexes are not logged, because in-memory OLTP design in architecture, every time SQL Server starts, indexes are built again. So there is reduced logging that SQL Server benefits from, but that gives you marginal improvement in terms of performance. That's not really such a big deal, because there is full logging with your data. It's only indexes that you benefit from. So in-memory OLTP architecture, there are other things that you can really benefit from. For example, natively compiled store procedures. So if you are really moving your data into memory optimized tables and you're rewriting your T-SQL procs, using natively compiled stored procedures, and the combination of that is really deadly. That would give you great performance improvement, but those are other aspects of in-memory OLTP which is like beyond this session. But there are that's the reason why you see reduced logging here. Well, so in part 3, as you see, this is where the crux is. Now, the beauty of this demo part 3 is that if I change my clustered index from GUID to order date, I will again start getting performance improvement. And you could just see a sense of number here that I had put in one of my previous demos. When I changed the GUID from when I changed the clustered index from GUID, which is a unique identifier data type, to order date, disk based test was giving me 60 seconds and in mem was 20. So I was getting 200% performance improvement. Well, this is, I'm not going to run this again because it is going to be a repetition, because this is similar to doing this, because in our previous runs order date was the clustered index. So I'm not really going to do that. So let me go back to SQL here and show you the wait types once more. And now you can see after multiple runs, write log is still the topmost wait type. So we got to address this before we see any performance improvement with memory optimized tables. So that is part 3 of the demo, where you see that there are bunch of these candidates that are not good candidates at the moment. Issues, performance issues lie somewhere else. So first let's go and fix that, then try to get performance improvement with in-memory OLTP. Hope you enjoyed the demo and they were useful for you to get all the concepts clear. And I would just like to go back to the takeaways just to make sure that we've covered what we talked about, which is we talked about the performance principles. And as you see, latch-free design is the key essence. You saw how you can benchmark performance using simple tools and the favorite spreadsheet Excel. You also saw how you can simulate near real workload using the tools and how you can populate your databases with a lot of data. And of course, the final thing was how to identify good and bad candidates for in-memory OLTP. With this, here is a small summary and call to action. You can connect with SQL Maestros. The Twitter is @SQL Maestros, and likewise Facebook SQL Maestros, and YouTube also has the same name, SQL Maestros. If you wish to connect with me, I have a personal website, amitbansal.net. I am available on Twitter also, @A_Bansal, and other Facebook and LinkedIn URLs are all out there. If you have more questions about this session or SQL Server or in general Microsoft Data Platform, there are two very good groups that you can join. I'm sorry, I just skipped a few slides forward. So that's the group you should join, facebook.com/the SQL Geeks. And there's another LinkedIn group. So that's the group. If you see the second one, linkedin.com/groups, and that's the number. So the PDF will be available to you. So you could just click on the link and join these two groups. They're wonderful knowledge sharing and Q&A platform. A quick word about SQL Maestros. So as we do a lot of training and health check and on-site deliveries, do visit sqlmaestros.com to learn more about everything that we do, or just drop an email to classes@sqlmaestros.com and someone from the team will revert back to you. And pay special attention please to hands-on labs. That's a wonderful learning platform. I believe the best way to learn is to do it yourself. And here is a repository of more than 100 labs. A hands-on lab document is a very guided step-by-step document with exercises, illustrations, graphics, and explanations, and you can practice a lot of these topics. So we have more than 100 labs. You're trying to cover SQL Server, Azure, data science, BI, advanced analytics, many topics. Just go and create your free account or drop a mail to holsales@sqlmaestros.com and someone from the team will get in touch with you. If you wish to join Data Platform Geeks community, it is a community of more than, as on date, more than 2 lakh data and analytics professionals, and we try to make all our videos, webinars, many labs, all free on this particular website. Just go and create your free account for yourself. We keep doing a lot of in-person events and webinars across the globe. I already talked about the groups, so most welcome to join the group as well. Finally, don't forget to visit dps10.com. I hope to catch some of you at this conference in the month of August, and it will be lovely to meet you in person. That's it for the time being. You can follow me at @A_Bansal. Thank you very much for your time, and you have a great day ahead.